A classical treatment of probability is for a known population where you know all the outcomes. This is also known as a theoretical approach. Because you know all the outcomes, you don't need to run experiments. So again, we've got the calculation. The probability of event is the number of outcomes favoring the event. So that's a known figure. The total number of possible outcomes, that's also known. So we can calculate it. So let's take a look at 3 examples. The first one is tossing a coin. What's the probability of a tail? So the probability of getting tail. The total sample space n, it's capital N because it's all possible outcomes. There's only 2 outcomes for tossing a coin, heads or tails. The favoring event we're thinking of is a tail, so that's one of those 2 events. So that means it's 1 over 2 or 0.5. So we know that there's only one tail on a coin, and we know that there's only 2 sides. So we know in advance, so we can work out the calculation theoretically. Similarly, for a die, if we throw a die, what's the probability of getting a 3? There are 6 sides to a die, so there are 6 possible outcomes. One of those is a 3, so the probability is 1 in 6, or 0.166. And the same goes for selecting a card. What's the probability that we'll select a jack? There are 52 possible cards, 4 of them are jacks, and we can work out a probability from that. Now it's important to note that this is the theoretical approach. This is what will happen in theory. This is the real probability. In practice, of course, if you toss a coin, you might toss a coin 3 times or 4 times and get a tail every single time. But if you actually ran the experiment of tossing a coin or throwing a die or selecting a card to infinity, if you did it a very large number of times, the probability that you would actually get would always come towards the theoretical figure. So in practice, although we call them experiments, we don't need to work out the experiment for these known probabilities. So that was for a known population. The alternative is for an unknown population. This is known as the empirical approach because we don't know what all the possible outcomes, and we do actually have to experiment. And this is much more relevant to statistics. So this is the kind of probabilistic calculations we're going to be doing in statistics. Again, the probability event of the number of outcomes favoring the event, E, and then the total number of possible outcomes, N. In this case, N is not all possible outcomes. We don't have the full population. It's just the number of outcomes in a sample. So an experiment will involve a finite number of trials. So take the example of a random sample. So that's what we typically do in statistics. We don't see the whole population, we just take a small sample. So the probability event that of a group of people that a person will have blue eyes. The sample space, N, large N, the total number of people is unknown. So we happen to take a trial of 100 people, and we find that 30 of them are blue-eyed. So from our sample, we set N to be 100 because that's the sample size, and we found out that E was 30 by counting, and then we found the probability that a person is going to be blue-eyed from this is 0.3, 30 over 100. As you can see, this calculation of the probability is exactly the same as the frequency table. So if we ran a frequency table of people with eye color and we only had blue and brown eyes, we would get 30 are blue-eyed and 70 are brown-eyed, and the frequency would be the relative frequency would be 0.3 and 0.7. So relative frequency and empirical probability are the same. Reporting probabilities. It's important to note that the theoretical and classical approach are both objective. However, an alternative subjective probability. We might ask an expert for the probability of an event happening where we don't know what E is or N is, and we can still use that figure because it'll be a number between 0 and 1. We have to report or express probability, and there's a number of ways of doing that. So for instance, the probability that a student is blue-eyed, we can express that as a proportion, so we can say it's 0.3. So 0.3 of the students are blue-eyed. We can express that as a percentage, 30%. We can express it as the odds for something, as in gambling odds. So it's 30 to 70 or 0.43 to 1. And the calculation is equal to P over 1 minus P. We can also express it as the odds against, which is 70 to 30 or 7 to 3 or 2.33 to 1. which is 1 minus p over p.